Yeah, so basically my objective here, I'm not so much going to give you many new research results, but basically what I want to help everyone with is basically as you're using M-Cube or even similar millimeter wave systems, uh, basically this is some mostly going to give some practical ideas and advice on how do you implement the baseband part of the processing. So generally with M-Cube, this is the kind of setup that you have to have. So you need the baseband processor is the part that it's kind of interchangeable, and then we have an RF section which the RF part you sends and receives the actual RF data to and from your baseband processor, and then we have the separate phased array controller at the bottom here, and so this phased array controller at the bottom here, that's the other part of the system. And so the baseband, if we're doing real-time processing, the baseband needs some way to synchronize with this phased array controller. And that's really the only other major requirement of the baseband. So then the phased array controller is controlled over USB. We'll talk about that briefly later. And so we basically have two kind of major classes of basebands. So one is the RF sock. Actually, in the original paper, we used something kind of a similar FPGA based solution that had 1 gigahertz of bandwidth instead of 4 gigahertz. So the advantage is basically that we get a very large amount of bandwidth. This lets us try out all sorts of different things like high resolution radar. You can operate communication protocols in a similar manner to how they would actually run in the real world, whereas most of the standard SDRs can't really do that. So if I remember correctly, the 802.11ad operates with about 2.1 gigahertz of bandwidth, which is, to my knowledge, most of the kind of prepackaged SDRs can't do this. The disadvantage is that to achieve the full bandwidth, we have this custom adapter board, which I'll show you later, that we need to use. None of the boards that shipped from Xilinx actually have the connection hardware that you need for using it in a baseband configuration with a bunch of RF chains. So it seems that's actually pretty common for people to have to develop these custom daughter boards to actually achieve this baseband connection. The other big disadvantage is that let's see, I forget how I calculate it. I think this is if you're using all eight possible RF chain, or all 4 possible RF chains, you get a very large amount of data. So in this case, I calculated a peak, you can get about 384 gigabits per second of raw data. And it's very difficult to actually process that much data in real time. So generally, you need to do some sort of, even if you're not using that many RF chains, even if you're not using all of the RF chains available to you, you'll still often need to do some custom programming because you can't offload that much data in real time. So you need to figure out, either you need to somehow reduce the amount of data by doing some of the processing on the FPGA, or you need to for example, what we did with the radar, the digital radars, we basically turn off reception once the buffers are full, wait for the buffers to empty, and then turn back on the radar again. So those are basically your options, the basic options you have for doing the FPGA programming. But the problem is that for most of your applications, you may need to do some custom programming based on what sort of data you want to get out of the FPGA. So the other way that you can interface, that you've probably, if you've been working with M-Cube or even with some other millimeter wave software radio, you've probably used the standard SDR. So we've been using the N310, B210, and Warp SDRs previously. So the big disadvantage is that it limits the bandwidth. We also, there's the image problem, which we discussed in the paper a little bit, but really the problem is that generally you can't use the full bandwidth that real communication system would use, and you can't, or even a real radar system. Yeah, so this is our custom board that Kai actually developed. Well, Kai and then one other student developed, which you can see attached to the GC111 board. We could actually use a very similar board on the newer RF socks. I don't think we've fabricated that board yet, though. So basically, the board itself is pretty simple. Basically, on the transmit path, we just have what's called a balun, which converts basically the RF sock outputs a differential voltage from its DAC. So for our coax cable, it doesn't want a differential voltage. It wants a ground and then the power. So the balance do that conversion, and then on the RX path, basically we basically just have a baseband amplifier with an adjustable gain. So these dip switches that you see here let us adjust the gain. And it also, there's something in there, I forget exactly what. Basically, there's a aliasing filter in there as well. And as before, it takes in a single-ended connection, outputs a differential connection for the FPGA. So this is how the radar, the digital radar baseband worked. So I actually omitted something here, but basically we have a configurable waveform generator that generates the FMCW waveform in real time. Basically all of these RF socks have a built-in ARM coprocessor, and that processor can access certain settings on the FMCW waveform as registers. And then yeah. So actually, Flavio sent one of the products. We've looked at this as well. I think so. I think this works. There's a product from Avnet that is designed for millimeter wave development. If I remember correctly, I think it works around 28 gigahertz. So unfortunately, it's not really suitable for. So basically, their daughter board directly up, if I remember correctly, directly up converts. You can correct me if I'm wrong, but I think it directly up converts the signal to 28 gigahertz. So it doesn't. If you're doing stuff with in the 28 gigahertz range, it's probably useful. As far as I know, though, it's not compatible with 60 gigahertz. Yeah. So, anyways, so the FMCW generator is then we synchronize it with a DMA buffer. We synchronize the timing of the FMCW generator with the receive side, which is a DMA buffer, and that passes the data back to an ARM controller, which then sends and receives data from host PC over gigabit Ethernet. And really, previously, this ARM controller, this ARM microprocessor was our main bottleneck. So especially the DMA to the ARM microcontroller used a Xilinx, use the Xilinx IP core, which has some significant limitations. So basically, we couldn't. The data rate that we could actually achieve, I think, was well under 10 megabits per second. So let's see. Cool. So Ruchyeong, do you? I guess you can present. These are your slides.
Yeah, maybe I will just talk some. Yeah, I will.
Do you want to stay closer to microphone?
Yes.
Oh, yeah. So, well, with this constraint that we want to achieve somehow real-time applications, we want the throughput be higher, so that we just remove the DMA, so that we do the processing basically in FPGA and send out the data via 10 gigabit Ethernet to the PC host, so that the throughput can be enhanced. So, well, in this example, then we do the channel impulse response estimation, so that we do the packet detection, boundary detection, and the algorithm sequence aided channel estimation within the FPGA, and do the packetizer to pack a UDP package so that we can send it via the Ethernet to the PC. So in this way, that we can achieve a throughput near 10 gigabit. So that we can somehow achieve a real-time application if we do not send packets so often. So that's well under the 10 gigabits threshold. So we can do that. Yeah. And also I think the next slide.
Just a minute. Yeah, so just I guess to summarize what you're saying, basically, so we're doing two things here to improve, basically make our system real time. The first is that we are reducing the amount of data that we actually need to send by doing some of the processing in the FPGA, and especially things like packet detection. So if we do packet detection in the FPGA, we can basically throw away all of the data that isn't a packet. And that significantly reduces the amount of data that we need to send. And the CIR estimation also does similar things. Basically, we don't need to send every single sample. We can send a much more limited subset. And then the second thing is we are bypassing the ARM processor. So even a 1 gigabit Ethernet connection would be an improvement, but the 10 gigabit Ethernet connection in particular lets us send a lot more data. So those are kind of the two key things: is we're increasing the size of our output data pipe, and we're also reducing the amount of data that we need to send through it.
Well, yeah, this is the block diagram of the basic design. So it involves a lot of clock domains to do the work, so it can somehow cause problems, and everything needs to be arranged carefully on the FPGA. Otherwise, it will complain a lot about the timing issues. So we have AXI settings so that we can configure different module parameters on the fly, so that we want not to change the FPGA code and synthesize it for several hours. So we can adjust the parameters so that we can see how many cycles we need for the packet detection, and also some threshold that we actually need to use. So this code is so this implementation is actually adapted from the MIMO RPH project. So that's really helpful for the implementation here. And we now achieve the sampling rate of about 2 gigahertz. So it's now the AD standard, and we can that's super sampling rate of 8. So we can get the required data and use FIFO to buffer some information. Yeah, because the speed of CRR is still faster than our 10 gigabit Ethernet, so we still need that, and to combine with the timestamp and also noise estimation during the header, so that we can get all this information and packetize and send to the Ethernet port, and then the thing will be done. I think it is a lot of engineering work actually. Yeah, to get all these systems work together is really difficult. Yeah, I think.
One more.
Oh yeah, this is the loopback test on this U111, so that we can find that loopback. So the channel impulse response starts in the middle. It looks I think it's quite clear. So this says that this system basically works. We haven't actually attached it to the MQ platform, but I think that I will do that later. I also have a little program at the PC to receive the UDP package and to process the package in real time and convert it to a data set file format with compression. So it will generate large data sets very quickly. So it will for one TX, one RX settings, it will create a 5 megabyte file data set for channel impulse response within several seconds. So there are a lot of things to do actually at the PC side. So maybe more processing on FPGA, so or something interesting to do the filter thing at the PC so that we can have a smaller data set for our real use. Yeah, I think that's my part.
Great, yeah, thanks. Yeah, so I guess one other thing, so I think people have questions about how the N310 baseband works as well. So really the key, so I guess this is for all of the USRP based basebands. Really the only thing we're doing different from normal SDR is we use what are called the ATXR registers, so the automatic transmit receive GPIO. So what that does is and actually internally I think it's inside the FPGA where the FPGA will, right at the moment where you start either transmitting or receiving from this FPGA, it will flip the state of one of the GPIO outputs. So this is suitable for at least 100 nanosecond level synchronization. I think actually a bit better than that. And so then based on that, we can get these real-time beam scans. Basic uses. So I put up a MATLAB interface that you can use on GitHub. Originally, I actually wrote this before MATLAB supported the N310. So this is kind of a workaround for the lack of MATLAB support for the relevant hardware. MATLAB does now support the N310. I'm not sure if it properly supports the GPIO settings that we're using. So it may still be necessary to use a package like this. Yeah, so just a few notes. So the TX and RX gain that you set here, those are, you should normally set those based off of the frequency response curves in the USRP data sheet that you're using. Some other notes on kind of the internals of how this works here. So one of the key limitations right now is that right now we save some of the data in a RAM-backed file system, this is one of the things that will only work on Linux. We also, the USRP is held as a global variable due to some limitations in how the MATLAB C++ interface works. So those are just some limitations to be aware of. So it's probably possible to run this off of Linux, not on Linux, but it will take some modifications. And the same thing goes for this. It's probably possible to have this separately separate objects that refer to different USRPs. But currently the program isn't really set up for that. And finally, so these are common issues that both we've run into and just from emailing people who are using MCube. Some of these issues seem to be common with other people as well. So this is just, I want to throw this in as kind of useful troubleshooting workflow. So obviously one of the biggest issues that you'll have if you're trying to do millimeter wave communication is underflows in your software-defined radios. So that happens when your some part of your network interface can't keep up with the number of samples that you're either sending or receiving. So basically when this happens, you have to, the solution is to reduce the amount of data that you're sending and receiving. So there's a few different ways to do this. One is you can reduce the number of samples you're sending at a time, which often works best. You can try to reduce your sample rate. But kind of this is one of the things that has motivated us to use the RF SoC is you can often work around these underflow issues by basically programming in custom logic on how to handle the data that you're using. Another issue that shows up a lot is basically your SNR. Like maybe you're receiving the data, but your SNR is only 12 dB. Or actually no, 12 dB is somewhat good. If your SNR is if you're receiving data but your SNR is down near 0 dB, often what's happening is that you are dealing with phase noise. So basically these millimeter wave devices have very high phase noise, and if you're using an OFDM waveform, this basically this increases the noise floor on basically each subcarrier. So the way that you want to fix this is you want to increase your subcarrier spacing. So you can do that by increasing your bandwidth, which could cause an underflow, or you want to reduce the number of subcarriers that you're using. So this has actually shown up both in our 60 gigahertz work and some of our more recent 28 gigahertz work. And finally, this is something that both for us and some other people seems to happen a lot, is you need to be aware of, if you're using the same USRP to both transmit and receive, you have to be aware that basically even if nothing is attached to your device, there's basically some coupling paths running through the USRP that can cause the transmitted signal to end up at one of the receive ports, even if there's nothing attached to either of them. So this is something to look out for. Generally, if you increase your transmit power a lot and suddenly you see that something's being received at the receive side, often that just means that there's kind of this coupling path through the USRP, which is how the receiver is getting the signal. It's not actually going over the air at all. So this is something you kind of have to be careful with. I don't know how many times we've run into this, but basically you do need to make sure. One way to verify this is, for example, you could either unplug or switch off the RF interfaces and see if you get the same result. One thing that you can do to mitigate this, so if you do want to use one USRP or one software radio for both transmit and receive, on the USRP, the N310 has two separate daughter boards. So often, if you're only using two transmit chains, for example, you can use the first two ports only for transmit and then the other daughter board only for receive. That will reduce some of the self-interference that occurs within the software radio itself. And finally, so this is just some frequently asked questions around how the control FPGA works. So basically, the control FPGA basically just has a big lookup table containing an array of beams and gain values that it will switch between over time. And then it has a few registers that say how frequently should the beam switch and how many beams, basically what's the length of this array. So the maximum interval between beam switching is around 5.5 milliseconds, which, as we'll show in the next slide, can sometimes limit your beam scanning options if you're trying to scan a very large number of beams. The maximum length of beam sequence is 4095. And the other thing to note is that each different phased array can have a separate time between beam switching. So this is kind of a more sophisticated example that we used. In our paper, we had we wanted to demonstrate 2x2 MIMO. So basically, we can't scan. Let's see. I think we had. So NCB I think was around. So I think we had around 16 beams. So if you want to calculate 16 to the fourth is a very large number. We can't scan through all of those in a single real-time data collection round, both because of the software radio limitations and the phased array controller limitations. So what you see here is we scan through the transmitters. The transmitters have different, if you look here, they have different timings for when they switch the beams. So we'll scan through all of the first phased array beams before switching to the next beam on the second phased array, and so on. So this is just if you want to do something like this where you want to scan all the possible beam combinations, this is normally a pretty good way to do this. Yeah, I think this is all that I have. So does anyone have any questions on anything relating to baseband programming?
Thank you, Tim. Any questions regarding the baseband program?
Do you have an actual send and receive function for like send the binary sequences and then receive it? Here.
You mean this function? The function for the N310 data transmission?
Right. It looks like the third command or the third code that you use. You send a TX data over. Is that over the air?
Yeah.
Okay, and then you kind of receive the data at the receiver end.
Yeah, so the idea is that basically the two are kind of roughly synchronized. So you're transmitting data and receiving data at the same time from the same device. So it is possible to use different devices. It just ends up being a bit more complex usually.
It's true. So the TX data in the parentheses is like any random sequence of the data.
Yeah, so it's the samples. It's the samples that you want to use. If I remember correctly, it's floating point. I'm trying to remember. I think it's scaled to between ±1, but I would need to check on that.
So when you say predefined sequence, is that like you cannot change it at all, or?
Oh, yeah. It's only when I say predefined, I just mean that you define the transmit sequence before you run the function. So like it can't be. So I think in the other MATLAB USRP interface, it's a bit more real time. So you could, in theory, adapt the transmitted signal as you receive data on the receive side, but that's not possible with this. So that's that's a minor limitation for most of what we want to do, but it's something to be aware of.
Right. So if you have like geographically separate the TX and RX, right now it's quite challenging to do so, right?
Yeah. So the main so there's a few different ways to solve the main problem is that you need to in general you need to synchronize the data transmission and reception somehow, and it's basically because the USRP is limited in how much data that it can send. So basically if for the most part you can't just leave it running indefinitely. If you'll start to see lots of data being dropped basically if you let it run for too long. So somehow you have to have them running at about the same time. So it's possible to do this.
Right. If you have if you have some kind of like preamble stuff, and then that can handle the synchronization, and then you do the decoding probably offline, that might be possible, right?
Yeah, but so actually the problem though is, so your preamble detection then has to go back then has to direct the received beams. So assuming that you're scanning the received beam, you need to send your preamble detection symbols, preamble detection signal somehow that needs to control the phased array receive scanning. So that's really where it gets a bit more complicated. It's certainly possible to do this, but there ends up being a lot of things that make that complicated. So for research purposes, actually what we're looking into is mostly, instead of doing that, we can we can either use a pulse per second signal or a GPS-based synchronization to pre-synchronize the time at the transmitter and receiver, so that we can get basically the beam scanning times at the receive side are close enough that we don't need to worry about synchronizing we don't need to worry about trying to use the preamble detection to select when to scan through the received beams. So that's kind of what we've settled on right now, is using kind of an external synchronization source. But yeah, it's certainly possible to do something else. You just need to set it up carefully. Or if you're using an omnidirectional or quasi-omnidirectional receiver, then you don't really have this problem. You can just so in fact, lots of the USRPs, you have some sort of functionality that you can use for built-in preamble detection. So you can just use that if you're using the omnidirectional receive.
Thank you.
Any other questions for Tim?
I guess one question with the on the last slide that you had for the control FPGA scanning. Yeah, so will this change all of the RF chains at the same time, or does it do it sequentially?
So okay, let's just a minute. Let's see if I can do a drawing here to make sure I understand what you mean. Let's see. Okay. Oh, good. Okay. So my understanding of what you mean is basically, do we send all of the control commands at the same time, or is there kind of a single thing, a single data writer that we multiplex so it kind of writes it like this?
Yeah, so sequentially, so that's why.
Yeah. So it's all, it can be all simultaneous if you want it to be. So we have basically the FPGA has separate, each RF chain has a separate module within the FPGA that controls it. So basically, when you set this up here, each phased array basically can get its own entirely independent set of timings. So they are synchronized together.
Okay.
But if you want, so the clocks are synchronized, but if you want to set a different interval for updating the beam, that's entirely fine.
Okay.
Yeah.
Okay, I think that makes sense. Yeah.
I do have one very trivial question. How do you handle the version difference between MATLAB and then Linux, for example, on the SDRs? Do you like switch back and forth?
Oh yeah. Yes, we've run into that problem. I'm trying to Renji, do you remember what we do for this? I'm trying to remember how we fix this problem.
Oh, what kind of problem?
Okay, I'm pretty sure what you're referring to is sometimes like UHD is built with a different version of libstd C++ than so MATLAB and UHD are built with different versions of libstd C++. like the C++ standard library versions.
Every time I use MATLAB, I have to flash a different firmware. And then every time I switch back to
Oh,
Linux, I need to flash another version of firmware.
I think that's not exactly the same case via
yeah,
Mist.
that's a different problem.
But via Mist, what we met is the UHD version for GNU Radio.
Yeah, I have the
and
same problem
UHD
too.
are different. So when you're using GNU Radio, it has its own version
Yes.
also for. But if you just install the UHD and then use MATLAB, MATLAB should just use. So at least for our interface, we just use the UHD you have installed. So there's no
Yeah.
such kind of problem.
So your programming is basically MATLAB is not that much you like the GNU Radio.
No, so what Tim has done is that he write the C code directly calling the UHD and use Max to compile it. So when you're running it in MATLAB, it will directly call the API from the UHD you have installed.
So are you using the MATLAB and or MATLAB USRP toolbox from MathWorks?
Right.
Okay, yeah. Yeah, so I guess we're not familiar. We don't currently do that. But yeah, I mean the big I'm not. I think the only good solution to this is to try to make sure you have a single common version of UHD, because like if I remember correctly, you can swap out the micro SD card for part of the firmware, but part of the firmware is burned onto the FPGA, and that's
I will not suggest to do that. Have multiple SD card. For each one, you have one of the version. That is much faster than doing that.
So you basically you have to compile from the source code, right? I remember I have the UHD or GNU Radio installed with like simple command, and that doesn't quite work out at the end because of
yeah, well, it's because MATLAB likes to package its own versions of libraries, so the Linux version will be different from the MATLAB version. Yeah, so I don't know if there's. Wait, Renji, were you saying that you can just swap out the SD cards or not?
You can just have multiple micro SD
Yeah.
card, for example, for the input.
The one thing that I don't remember is whether there's also does swapping out the SD cards also change the FPGA programming?
Yeah, I think so.
Okay, yeah. So if that's the case, then that should work fine. But yeah, I mean, I think the solution that we've settled on is mostly just to find a UHD version that works, then try to use it everywhere and not change it. But if that doesn't work, then yeah, probably try swapping out the SD cards.
Okay, thank you. I mean, we can discuss more details in offline.
Yeah, sure.